supposed to be due this week, since that's like all the details you're going to need are going to go up for that. You're like probably, like I said, I don't want to say before Friday. I'm going to say that that's going to be 2 weeks from Friday. And then the assignment that would have been distributed this week will be 2 weeks from that. So basically, you can think about everything just moving back. I would think probably, since it's going to be on Friday, as a result, like 2.5 weeks.
Okay.
Yeah.
All right.
Or at least that's my guess right now. It might be a little bit longer. It won't be shorter. It will not be shorter than that. But it might be a little bit longer, but it will not be shorter than that.
Okay. Thank you very much.
Yep. Yeah. Yeah. Like, I don't want anyone to stress it. I don't want, like, this is a stressful enough time for everybody. I really don't want anyone freaking out about this. Like, the assignments are generally, they might be work, but they're not hard. And in terms of assignments, like, the final individual written assignment is definitely hard, right? And it's definitely something that you're evaluated on. And I want to make sure that we're everywhere we need to be for that. But the individuals or the team assignments, like, again, like, as long as you put in a good faith effort, you're going to get a good grade. Maybe not a perfect grade, but a good grade. You're going to get a very good grade on those, as long as you've turned in something like that you as a team have put effort into. So don't worry about that. Do not worry about that. That part's going to be fine. And again, it's taking an unusually long time this semester, just because things are particularly unusual, at least for me in particular. But I'd say, oh my God, I don't think there's a single semester that I have been teaching this class in 4 years that everything has gone on time. So don't worry about it. This class, like, it takes a while to get us everything into place where everybody can do everything they need to do. So today, like, we're just going to, like, kind of go over the basics of the levels of measurement. We're probably not going to be working on the coding skills this week. I'm going to post the additional, like, sort of JASP tutorial, like I said, probably by Friday is my plan. And then next week, as part of the live session, we'll do whatever the class is, which will be a relatively short class, and then go over sort of a live screen shared feed on how to use JASP. And to be fair, like, I just want to be clear, once we get to that, JASP is not hard to use. I guess the one thing to be aware of is, going into this, if you have a very old if you have a very old very old computer you're going to be working on that does not have a recently updated operating system, it may be difficult to install JASP to run. But I'm going to give instructions on how to install JASP both normally, if you haven't already, and how to install it as a disk image if you have difficulty installing things. And that should take care of almost everybody's problems. And 4 semesters to teach, well, okay, the 3 semesters that I've been teaching this, where we have been using JASP, only 1 person has had difficulty installing it as a pre-installed disk image. And that was the case where it was a very, very, very old MacBook that had not been updated in some time. So as long as you have a relatively recent computer, such that you have updated the operating system relatively recently, I don't think you're going to have a problem. But if you do, email me and we will try to figure it out. It's possible that we won't be able to figure that out, and you're going to have to rely on your roommates in very important and very meaningful ways. But we're going to try to figure it out. Like I said, I think unless you are in an extraordinarily difficult technological circumstance, it's going to be fine. JASP is pretty easy to install. It's pretty easy to work with. So hopefully nobody has to worry about anything. Okay. So
Sorry.
today we're, yes, yeah.
It just a note that it said that class would start today, again at 4, and I know that
Oh,
if
no, it did?
yeah,
Oh,
just
did I screw up in because the ad, sorry, the headline should have said 3:30.
okay, just because I know a few people like I get flustered if like I cited and the teacher's already talking and then I feel like I missed something. So
Yeah. Well, you haven't missed anything significant yet. Um, we're just talking about sort of like background things so far. So so don't get flustered. And again, like anytime there's any confusion, I think that's probably going to happen just because this term is weird, right? This term is very, very, very weird, and you're
yeah, I just wanted
probably
to let
underprepared.
you know.
Yeah, you're underprepared for it, and I am definitely underprepared for this semester. um, you know, if there's any difficulty, any confusion, don't worry. And I'm just going to reiterate for people who are joining a little bit later than everybody else. I am attempting to record this one. I certainly hope that it's recording. It's um, Zoom is telling me that it's recording this. So I am going to, assuming all goes well, this is being recorded, and I'm going to be able to find the place on my computer where it's being recorded and uploaded. And so depending on where it goes, I'm either going to upload it directly to Zoom, or if this is too long, because I found that video is often too dense to upload, like the Moodle will often reject those. I will upload a link to a YouTube or some other repository. So don't worry about that. So everything that has been said today is definitely being recorded. So you're coming in a little later. If you if there was any concerns, hopefully everything will be available. And if not, like I said, well, like I've said before, I didn't say it this week, uh, but we'll be able to talk about things on Skype or by email as we move forward. Just do not be afraid to schedule an office hours appointment with me. Um, no one in this class has so far, but we're a little less far advanced as far as like what we're doing is. But my human resources class, I've got several meetings scheduled this week for office hours with students there, and that's totally cool. It's no concern. Like I said, like my office hours are totally by appointment this semester. So if you need an appointment to talk about something like for an assignment or any aspect of the course, send me an email and we will try to work out a time to meet with you. Probably by Skype if you have it, and if you don't, we'll figure out some other approach. We'll set up a Zoom meeting if need be, or something along those lines. So don't worry about those kinds of confusion things. Like, feel free to ask questions during class, like during these live sessions. Do not be afraid to do that. But if you don't want to do that, or if like you feel like questions that you personally have not been answered in the depth that you need them to be, just contact me and we'll try to figure something out for you. We'll do our best. Again, I can't promise anything. Like, I mean, even if this was a totally normal semester and you came into my office for office hours, I can't promise you that anything would be 100% comprehensible. But we'll do our best. You can ask questions, and we'll just keep fighting with it until it makes sense. So there you go. So we'll move on to just this concept of like what we're trying to do today is to talk about how to analyze our data. In this case, we're going to be talking about quantitative analysis. So we're not going to worry too much about any of the extreme details on this. Like I said, we're going to talk about accepting versus quote unquote rejecting hypotheses later on. Oh, once again, I got a chat. Oh, post. Oh, wait, hold on a second. That's supposed to go to everyone. Sorry. There we go. Oh boy. Sorry, I'm trying to answer a question that was sent to everyone, but it was going out privately. So sorry, it seems there's some problem because I really thought that I was, oh boy, telling people that this class should be 3:30 today. Anyways, just to be clear, class started earlier today. It was at 3:30, and that should be where it's out for the rest of the semester. And I thought I really thought that that I posted it to everyone earlier today. So if that didn't come through and people were confused, or if I screwed up, I'm really sorry.
It posted, but it said 4 p.m.
Oh, 4 p.m. Really? Oh gosh, darn it. Oh, I must have really screwed up from there. Because I really thought that I wanted to do exactly what I did last week where it was supposed to be 3:30. So I must have my attempts to automate things have clearly failed horribly. And I'm sorry about that. So thank you for letting me know. I'll have to check my on job to make sure that that everything is fixed up for next week. But if you're here now, just assume that next week will be 3:30, and the only reason it would be different is if I posted something to start the live session earlier. So 3:30 next week, unless I attempted to do it earlier, which just given the schedule with kids and everything, I can't imagine it possibly happening earlier. But that's the only reason. So it should be 3:30, if not earlier. So there we go. Thank you for letting me know that. I will try to make sure that things are fixed so that when it updates, it updates correctly, because I really thought it was supposed to be saying 3:30 this week. And maybe it's just like I may have different fields saying different things and they're not updating correctly, and that's a total screw up on my part. So sorry about that. So anyways, we're going to talk about analyzing data this week, which means we need to talk first a little bit about the levels of measurement. So levels of measurement, technically, depending on how you want to talk about this, there's 4 or 5. The 5th level is an absolute level of measurement, which we're not even going to bother with. That, like in this class, we're going to talk about basically nominal, interval, and ratio as it shows up on this slide. There's also ordinal, which I think the next slide, if I remember correctly, is gonna discuss it a little bit. But the basic idea here is how are we using numbers in our measurements, and so the basic idea here is with something like, well, the simplest level of measurement is nominal. So we've got categories, and so you just
sorry, sir.
hit me. Yep.
Is this the same slides we went through last week?
Shouldn't be.
Yeah, we did this last week.
Wait, we did this last week?
We did.
Oh my God,
Yeah, we
really?
did.
Yeah, you went through Kelvin and everything
We did,
with the temperature.
we did this last week?
Yeah.
Oh my gosh, I'm really sorry because that's, wow.
We
Wow,
are
I
at
don't, wow. Oh my gosh, my whole life is confusing as heck right now. Oh boy. So then let's just, then I will post new slides. They won't be up right now, but here we go. Then we'll just move on to statistical analysis. Which, give me a second here. Let me stop the share. All right, so you won't see me, but hopefully you'll hear me as I talk about that. Wow, oh my gosh. You know, the wild thing about right now is that every day is kind of like the other days, and is it is really hard to remember what's going on. So let me see here. Let's check. Let's check this one. Here we go. Yeah, this one will work. Okay, so I'm gonna share my slides again. And then this should be good. This should be good for this week then. And I'll post these slides. You'll have to wait until after this one because I'm gonna have to edit them a little bit. Because today we're gonna talk about, because that's what I thought we were gonna talk about today, but they were the wrong slides. So, and again, this is just the issue that as we're updating everything, the weeks are different. So I thought what I had there was the right one for this time. And since apparently the last week has completely fallen out of my head, here we are. So we're going to talk about mean differences today, and this actually is probably perfect because this is the one that leads most directly into to dealing with JAS. So this is perfect. So we're going to talk about what it means to look at the statistical differences between categories. And I just want to be careful with this, that here is probably the place where people get the most uptight is, so probably everyone here has run into or is familiar with the concept of the null hypothesis, right? So the basic idea with this is, and we're going to deal with this in kind of rhetoric in its simplest form, which is this idea mu1 equals mu2. And mu is just a term for the actual mean, right? So like the idea here is if I take a population of people, and let's just say I was actually able to get the entire population, the entire world, and divide them into men versus women and measure their height. The average height of men is mu1, the average height of women is mu2, or the other way around. That part doesn't matter. That kind of goes back to what I was just inappropriate talking about with nominal variables. Men versus women is nominal. It doesn't matter who's one or who's two. So we're just looking at grouping things together. So the mean in group 1 is equal to the mean in group 2. That is the null hypothesis. And null was just, in this sense, just saying like, well, it's saying that there is no difference between the two groups. That's all we're saying with a null hypothesis. We could, there could be more complicated things that go on there, and there are more complicated things that go on in like sciences like physics. But in general, we're not going to be doing anything more complicated than that in management. And then I'm not clicked on the right thing here. Here we go. So there are several possible alternative hypotheses, which is usually all abbreviated H_A or H_alpha possibly. So one of them is just the simple mu1 is not equal to mu2. You could also have mu1 is greater than mu2, or mu1 is less than mu2. And so what this is going to boil down to is whether, in terms of the statistical test you're dealing with, is a directional or a non-directional hypothesis. So of these, if mu1 is not equal to mu2 is a non-directional hypothesis. It's just saying, like, let's just say I have a big sample of male students versus female students, and I think that males and females perform differently in university. So we've got their GPAs. I could say it's just like, as a non-directional hypothesis, I'm just saying that male and female students have different GPAs. And you're not seeing anything. Like, you're not saying men have higher GPAs, women have higher GPAs, whatever. You're not saying any of that. You're just saying, I think that these are going to be statistically significantly different. Whereas the other two here, when mu1 is greater than mu2 and mu1 is less than mu2, those are what are called directional hypotheses. And we're saying, like, let's say, again, for the sake of argument here, we're saying that men were classifying as group 1 and women were classifying as group 2. So this first one, mu1 is greater than mu2, would correspond to the hypothesis that men have a higher average GPA than women. The alternative there is mu1 is less than mu2. We would be saying that men have a lower average GPA than women. So those are all possible alternative hypotheses. I would say that in management, the first one, the non-directional hypothesis, is the most common. We're just going to be saying, like, hey, these two groups are going to differ, and we don't really know what's going on there. But it could be, like, if you have based on your background research, your library research, the literature, or even your intuition, you have a good reason to say that one group is going to be higher than the other. You can go ahead and hypothesize it. And you might be wrong. That's fine. No one cares about that. Like, I mean, that's not gonna, like, especially as far as this class goes, that's not gonna make you get a bad grade. Like, being wrong is not a problem in terms of, like, statistics that you're doing. Saying things that are definitionally wrong or something along those lines, that could be a problem. But in terms of just being like, I made a hypothesis and it turned out wrong, that is not going to screw you up. I mean, to the point where it's like, with PhD students, you know, getting a hypothesis wrong doesn't invalidate their, like, you could have an entire PhD dissertation where no hypothesis worked out the way you hypothesized it, and you could still get the PhD because everything you said made sense up until the data. And that's where we are. Like, we want to make sure that you make sense. Like, you could say that men have higher GPAs than women on average because of, or you could say women have higher GPAs than men on average because of. And as long as your because of makes sense, then you don't need to worry about it. Like, for grading, you don't need to worry about, because it's like, you could say either one of those and the data could work out supporting or refuting your hypothesis. And that's just the way, that's as close to literally the way the cookie crumbles, in terms of anecdotes or things, as it goes. So all this is just different ways of forming it. So if you think that men and women are going to be different, but you don't know who's going to have the higher GPA, you would go with the non-directional hypothesis. That's that first one here. mu1 does not equal mu2. So in that case, all you're interested in is one is higher than the other. It doesn't matter which one is. Whereas the other two, in mu1 greater than mu2, you need mu1 to be statistically significantly greater than mu2 to support that hypothesis. And in the third case, you need mu2 to be statistically significantly greater than mu1 to support the hypothesis. And again, if anyone's confused when I say this, since no one's asking questions, I don't think anyone is, just in case, this symbol This U with the little foot on the front of it is the Greek letter mu, which is the standard symbol for a mean in statistics. Okay. So the general thing that I am going to say here is there are two vaguely different approaches to inference in classical statistics, and that's what we're going to deal with in this class, is what's called classical statistics, which is kind of funny because the alternative approach, Bayesian statistics, is actually older, but we're not going to deal with it in this class, and for reasons in that it's just much more complicated to deal with, even though arguably it is, according to lots of people, including myself, more correct. But under a wide range of circumstances, you're going to get exactly the same. Like the two major approaches to statistics, classical versus Bayesian, under a lot of realistic conditions, you're going to get very similar results out of them. So there's not really any reason to be particularly prone to one or the other. But within classical statistics, there's sort of two approaches that have been unfortunately blended together. And the blended together does cause problems. So there's a Fisherian approach, which is sometimes called significance testing, and the Neyman-Pearson approach, which is called hypothesis testing. Now, almost no one does either of these directly. So what you'll often wind up hearing is null hypothesis significance testing, which is, that's the default in psychology, management, every behavioral science, including economics. And so the basic idea there is pretty much you are doing something that resembles Neyman-Pearson testing, which is you're comparing your attained significance level, the p-value of the test that you've done to a particular level. Now, where that comes from is this blending with Fisherian testing, which is an arbitrary level. Like Sir Ronald Fisher was very, very clear that it's like, hey, if you got no idea what's going on, compare this to 5%. So in general, what winds up happening is you take a significance level from an Neyman-Pearson type test and you compare it to a standard level, which is coming from Fisherian testing, which is 0.05. And so in general, if you're not dealing with something very sophisticated, we're going to see is that people claiming that any result with a p-value, which we'll discuss exactly what that means in a moment, less than 0.05, which is 1 in 20 or 5%, is significant. And it's really hard to say exactly what that means without going into extraordinary statistical detail. The basic idea behind it is you can think about, like, if you did the exact study that you did many times, like thousands of times, more than 5% of them would yield similar results to what you did in terms of being greater than or less than the significance threshold that you set. And I said 5%, so it would be 5% in that case. So more than 1 in 20 of them would yield the same result. So it's very complicated. It's a very non-intuitive. So in general, once we get to it, it's best to just sort of, like, I mean, for most people, it's best to just sort of go with the rules of thumb. That if you've got a p-value less than 0.05, it's significant. If it's greater than 0.05, it's not significant. And in this class, we'll talk about this, like, gray area that we'll mention in a moment, which is, in fact, I'll just go ahead and go on to that moment, which is here. So levels of significance. So the likelihood of a relationship between variables. So if you've got a p-value, so here p less than 0.05, that's the handshake diagram here. Yep, that is, almost everybody would agree that that's statistically significant. I mean, there are a handful of very, very strict statisticians out there, probably Val Johnson being the most vocal among them, who would insist on a lower p-value. So something more stringent. So p less than 0.005 in 0.005 in Val Johnson's case. And then absolutely everyone, there's, as far as I know, no one would argue that you have a finding that is substantially worth talking about if your p-value is above 0.10. So this stop sign indicator over here. So saying no, we have any, there's nothing going on. It's just saying that there is no evidence in the data that you collected that there is any kind of a meaningful relationship between the variables. So p less than 0.05, people are like, okay, that's a pretty good indicator that something is going on. P greater than 0.1, people are like, no, there's probably nothing going on. And then there's this gray area. P between 0.05 and 0.1. People talk about this as being marginally significant, and that's acceptable in this class. But in general, I would argue, like, especially if you're going to go on, like if you're going to do a master's degree, if you're going to do a PhD, if you're interested in pursuing like consulting, like a job in consulting where you're actually going to be dealing with statistics, it's best to ignore this. Just set a level of significance and stick to it. But in general, this happens in the research literature, it happens everywhere, that there's this gray area, and it's usually between, so if you got like a p-value of 0.056 to 0.98 or so, that it's like, well, that's marginally significant. So it's one of those things where you would like round down to 0.05 or round up to 0.1, like that, as long as it's in between those things you call marginally significant. And that's the kind of thing where it's like the interpretation is essentially like, well, there's some evidence that there is a relationship between these two variables, between, say, your dependent and your independent variable. But it's messy. This study didn't do a good job of demonstrating that, or something along those lines. Where it's like, if you're resolutely above 0.1, most people would just be like, there is nothing going on here. Whereas below 0.05, people would be like, okay, there's good evidence that something's going on. And again, that doesn't mean that there is something going on. That doesn't mean there is a relationship between the two variables. It's just saying like, hey, your sample is saying that there's good reason to believe this. That there's evidence in the sample that to buy that, as opposed to, a non-significant result. So p less than 0.05, definitely significant. P greater than 0.1, definitely non-significant. And p between those two, so p greater than 0.05 but less than 0.1 is, people will often label marginal. But again, if you want to be stringent in this class, it's not going to hurt you to just say p 0.05. Even though it's an arbitrary standard, it is the accepted one. You could just say, like, if it's less than 0.05, it's significant. If it's greater than 0.05, it's non-significant, and we're not going to freaking deal with this marginal thing. That would be fine. And honestly, like, that kind of level of stringency, I think, is good. But the basic idea here is, as it says here, like the probability that P is the probability that I'll be making a mistake if I say there's a relationship between the two variables. That kind of hits on this idea that, what we're trying to get at is, if I say that variable A has a causal relationship with variable B, how likely am I to be wrong? And if so the probability that I'm going to be wrong and that is low enough, then you go ahead and say, yep, yep. So like what we're saying is like there's a, like if I did this experiment 20 times, only one time by chance would it come out this way. That's what the p less than 0.105 is, or, sorry, 0.05 is saying. That's saying that, you know, assuming that nothing was going on, this would be a very unusual result to get. Whereas a p greater than 0.1 is saying, well, that's not strange. That's not too weird. So like, so the basic idea is like, if nothing's going on, a very high p-value tells you, well, this is pretty probable under the hypothesis that nothing is going on. Where a very low p-value tells you, well, if nothing's happening there, if there's no relationship between the two variables, it would be weird to see a statistic of this level. And hopefully, like as we go through this, that'll make more sense, because it is like p-value is really subtle. P-value is something that professional scientists screw up. Even some statisticians who are out of the game screw up. And so it's something to be very, very, very careful about. So I'd say, like, for the purpose of this class, like just follow the rules on this slide, unless you want to get rid of the middle category, in which case you're just that marginal category of p less than 0.1, just get rid of it. Like it's perfectly fine to get rid of that. But if you're just going to like stick strictly to the way this class is taught, do the less than 0.05, less than 0.1, and greater than 0.1 categories as listed on this slide. Actually, I'm not going to worry about the refreshing work study this week, just because, you know, it can be. I think we got enough on our plate trying to deal with this, and so this is what the basic results coming out of JASP are going to look like. So in this case, what we're looking at is we're comparing GPA for men versus women, which is the example that I talked about earlier. So what you're going to be seeing here is there we go. So here, probably the most significant things we're going to be looking at here are the T and the P, and in terms of the actual statistical test. So here, based on some data from like another sample that we have in this class, we have a T of minus 1 point, let's just say 19, which has a p-value of 0.24. So, and this is like here in the middle, this is the degrees of freedom. For our purposes, we're not going to worry about that for this class. I mean, it's statistically important, but for this class, we're not going to worry about it. I'm just going to cross that right out. So don't worry about it. And we'll deal with how to get every piece of output that you need here in the additional material that I'll post later this week. But so what's going on here, and it will depend on how you've coded things. So in this case, I think it's men are scaled 1 and women are scaled 2 in the example that we're using here. So the fact that the T is negative is indicating that, and let's just check here. Yeah, that flows with what I'm seeing down below. That men, like the fact that it's negative is saying men have a lower average. But again, the T on its own doesn't tell us much. It tells us, and there are some nice things about T statistics in that they are very regular. So like once you get used to them, you can just look at a T statistic and see whether or not it's going to be significant. So like I can look at this one and see that it's substantially less than 2, like an absolute value, so it's not going to be significant. And then I go over to my p-value and then see, oh, well, it's definitely not significant. So yeah, that was right. So again, here, our t, I'm just gonna use the highlighter tool here, just be like, okay, here's my t value minus 1 point, let's just say 2, for the hell of it. And here's my p value, 0.23. So for this p-value to be statistically significant, and ooh, that's not good. Good look there. Here we go. Let's see, maybe this one will, yeah, there we go. Just gonna underline that. This would have to be a 0.05 or less for this to be statistically significant. So for us to conclude that there is any kind of like a real statistical difference between men and women. So in this case, we're seeing is like, yes, let's go down here where we're seeing, okay, there are 78 men in this sample and 125 women in this sample. The men have, very well, the men have an average of to say 0.3, and women have an average of 0.31. No big deal. For this class, we're not going to worry about standard deviations. We'll talk about them a little bit when we talk about reliability in terms of interpretation. We're not going to worry about it. We're not going to worry about standard errors. So here for this stuff, where we're looking at group statistics, all you're ever going to look at is what is the group. So we got males, and we got females, and just what the value is. So what the mean is over here. In this case, we see women have slightly higher mean than men, very slightly, like not even 0.07 or 0.07 grade points higher. And that's what's reflected up here in the t-test. So the t-test is just a sort of standardized way of talking about that, how big that difference is. And what it is it's the difference in the means standardized by the standard errors in a way. And you don't need to worry about that. It's just saying like, okay, there's a difference between these two things, and this is its size in standard error units. And over here, the p-value is telling you whether or not that difference is statistically quote unquote big. And in this case, it's not. Like the p-value is well above 0.05. It's 0.0 or 0.24. So that's quite a lot larger. That's almost 5 times larger than what we're looking for. So it's a big p-value. It does not mean much here. So like men and women, the conclusion from this is that there is no evidence in the data that we looked at here that there is a statistical difference between men and women in their GPA. Now again, down here we look at this, there is an actual difference. Like men have a slightly lower GPA than women do. That's just what happened in the sample. And this is the idea that, like, assuming this was a random sample between men and women, that assuming all of the mechanics of this random sampling, which we'll deal with in a week or two, that there's not enough evidence that the difference in these means is enough to say that there's a difference in distribution between men and women. And again, there's a lot going on here. There's a fairly larger sample of women than there are of men. Men have lower GPA, women have a higher GPA. There's a lot going on here, but just based on like a raw statistical interpretation, that again, I think like we could, if we wanted to pick apart in meaningful ways, all we're saying is, here's the t-value. Here's the mean for men. Okay, let me just get a different color just to be sure here. Here's the mean for men, 3.03. Here's the mean for women, 3.10. The t between them is minus 1.19. The p-value is 0.24. That's what you would say about this. So with this kind of statistical test, and we'll talk about this more in the coming weeks with the statistical test, we'll report the groups, their sample sizes, their means, the statistic, which is in this case the t, and its p-value associated with it, which in this case we'd say there is nothing major going on here. And here, just to illustrate this a little bit further, so like this stuff that I have now marked up horrifically, this is an example of the output from JASP, which we will typically be using in this class. Here is an output from SPSS. So here we have men and women differ in the types of strategies that they select to manage their energy, which goes back to the refreshing work example. So here we have, again, males versus females. We have 134 men versus 164 women. And we have a mean on this particular strategy, which is taking work-related breaks. We have a mean of, let's just say 4 and 4.4 for men and 4.3 for women. And again, we're not concerned with any of this stuff over here. And here, if you use SPSS and you can ask for this in JASP, it is not the default. The Levine's test for the quality of variance is arguably important, but it's extremely underpowered, so we're not going to worry about it. All we're going to worry about is this top t-test here, which is the t-test you'll typically get if you're doing JASP. So we've got a minus 3.05 here. Again, we're not going to worry about degrees of freedom, and it doesn't really matter for any reason. So we've got, either way here, we've got a two-tailed significance test of 0.003. All this other stuff none of this other stuff matters for what we're doing in this class. It can matter a lot in statistics. The basic idea here is what we're going for is, let me just erase all these marks that I've made. Oh wait, that one's already there. That one's not. That's not a mark I made. Huh? I had a lot of marks here. Okay, so I've gotten rid of these marks. So just to be clear, the idea with a t-test, and this is true of any test, but it's like very clear with the t-test, what we're saying here is this is sort of what a t-distribution looks like. It's basically a normal distribution. And what we're saying is that anything that's out in this tail or this tail, that's for a two-sided t-test, which is what we're typically going to use. Those are extreme, they're unusual, they're weird. So like if you have a really big on the positive side or a really small on the negative side t-value, which in this case, again, what are we at? We got a minus 3 and a bit. So that's over here, minus 3 and a bit over on this side. That's a really small, or you can think about it as a really large negative t-statistic. So we've got this pretty small p-value here, 0.003. Now, this is a two-tailed test, which I don't really like. We hardly ever use it in this class. It's about like, that's about saying like, if I thought that in this case, like women were going to have a higher GPA than men, and so it matters which we score this. So men are group number 1, women are group number 2. So women are quote unquote higher. So men, like if men have having the lower value, they're going to be negative. Again, it can be a real mess talking about this. So we're not going to worry about that. We're going to typically go with the default, which is a two-tailed test, which is just saying like, if one of them is unusually large, that means that it's going to be way out here or way out here. And if that's the case, then, and if it's way out enough to get us a p-value less than 0.05, which this is 0.003, is substantially less than 0.05. If that's the case, then we're going to say this is statistically significant. So we're saying like women and men differ in the types of work-related, the types of strategies they use to manage their energy. So women take, I believe, like according to the way this works, the women take more work-related, like longer periods of work-related breaks than men do in this sample, and that is statistically significant. Let's just pop to the next example just to look at it, just so we can see what's going on. So again, we have women differ in the types of strategies they select to manage their energy. So again, another t-test, recreational breaks. So men, 134 men, 161 women. Men's responses to this were 4. Let's just say 6. Women were 4.5. Here's the t statistic between them, 1. Let's just say 4. And here's the significance. The p-value is 1.17. So there is, so you see here, the hand is saying stop. There is no significant difference between this. Like men and women do not, although there is a mean difference, it's small. So like about 4.6 versus about 4.5. That's a different, but it is not statistically significantly different, which is what the p-value tells us. Saying, could be sampling, could be random error, could be whatever else is going on. There's not enough evidence here to determine this one way or the other. So here's the output of what if we had multiple groups. So instead of just 2 groups like men versus women or experiment versus control, this is what it might look like. So this is an ANOVA, and this is what the JASP output will look like. So here we've got a variable that has at least 3 levels. So instead of being men versus women, this could be like student, part-time, full-time, right? Or whatever we have here. So this variable called employee has at least 3 levels, which means that you can't just say like this versus this, it's this versus this versus this. And then pretty much everything else going on here is statistical and technical for us. So we're going to ignore the sum of squares, the degrees of freedom, the mean square. All we're really interested here is the F, which is hard to interpret. Like I said, like once you get used to it, the T statistic, and again, let me just erase some of this stuff just to make sure that everything's legible. So once you learn, make this green so I can draw another color. So if you once you get used to it, the T statistic you can start to interpret. Like if it's around 2 or larger, you know that it's going to be statistically significant, and that's just because of the way, like how symmetrical and regular the T distribution is. The F distribution does not do that. It is neither symmetrical nor regular. It depends highly on its degrees of freedom. So while you're going to need to, in this class, report your F statistics, so in this case 0.7878, it's going to be, you're never going to get you, like I've been doing this for years and I'm still not, like there's no way for me to just look at an F statistic and tell you whether or not it's significant. So yeah, so you're going to report the F statistic and its p-value, which in this case is let's just say 0.46, which is not statistically significant. So I'm just going to put a mark through this, just be like, that is not statistically significant. And then we're going to look down here at our means and their sample sizes. And those are the kinds of things that we're going to report if you're doing an ANOVA. So you're going to say there was, in terms of employment, so what we've got here is actually, people who are unemployed, who are working 20 hours or less, who are working more than 20 hours, right? So those are our 3 groups. And so we got 59 people who have who report no employment, 61 people who report working 20 hours or less, and 81 people who report working more than 20 hours. And so they have, like, in terms of the number of which recreational breaks. Everything go. Here we go. Yeah, recreational breaks. I thought that was what we were doing. But anyway, so what we got here is we've got we'd report 59 people here, like 61 people here, and 81 people here. We'd report their means as, well, let's just say 3.1, 3.1, and 3.0. And so the issue here is this is not statistically different. And so and the other thing to talk about here with an ANOVA is, despite this one not being statistically significantly different, what an ANOVA is telling us is that we have multiple groups. All the ANOVA is telling us is that at least one group is different from the others. So if this had been statistically significant, so if this p-value up here had been less than 0.05, what that would mean is that the mean, one of these means was, at least one of these means was different from the other two statistically. So that could mean that all three of them were statistically different. It could mean that one of them was higher than the other two. It could mean that one of them was lower than the other two. It could mean that this one was very low, this one was medium, this one was high. So it could mean lots of different things. Like the F-test in and of itself is just what in statistics we call an omnibus test. All it's doing is saying that one of the groups that we're looking at is different from the other groups, but it can't tell us what direction that is, and it can't tell us which group is different. We have to look at the means for that. And if we wanted, like if we had hypotheses about this and we really wanted to go into it, this is beyond this class, we wanted to test the pattern of the mean differences, we could do that using something called a contrast, which you can do in JAS. It's a bit of a pain. It's relatively easy in SAS and R, but it's a thing that you can do. And that's, we're actually kind of done with the basic ideas here. Like those are the critical elements here. So let's just take a look at another one, which is just saying, in this case, part-time workers will be most likely to take work-related breaks to manage their energy compared to both full-time workers and students. So the basic idea here is what we're saying with this hypothesis is that we have three groups of employees here. We have part-time workers, we have full-time students with no job on full-time work, all right? And so we've got 81 students who have full-time students who have no job in the sample. We have 95 full-time workers. We have 119 part-time workers. And so if you add all those up, this should come to, since there's nobody else, that should come up to 295 for our total sample size. And here are the means for each of them. So 4.1-ish for the full-time student, no job. 4.2 for the full-time worker, let's see, in fact, let's go as far as saying 4.22 for the full-time workers, just the full-time workers, and 4.18 for the part-time workers. All right, so those are our means. So like looking at this in the raw, what we've got here is that in terms of taking work-related breaks to manage their energy, the full-time students have the lowest mean, the part-time workers have an intermediate mean, and the full-time workers have the highest mean. And then again, for our purposes, although statistically this information can be useful for our purposes in this class, all of this stuff is just garbage and you don't need to pay attention to it. And then all we have to do is go down here to our ANOVA table, which again, of this information will be reported in JASP. All of this is SPSS here. This is all useless. We don't need to worry about it. What we're looking at here is our S statistic is 0.52, and the statistical significance, the p-value, and this will be called p-value, or it's called sig here, will be called p-value in JASP, which we'll be using, is huge. It's 0.6 basically. So like there are tiny mean differences between these, but again, like let's look at this at one decimal place. Full-time student job, that's 4.1. Full-time work is 0.42, and part-time work is 0.42. So again, there are minuscule differences between these, and we cannot see them statistically. Like with this sample, with a total sample of just under 300 people, we cannot see the difference. There is nothing going on here that we can see statistically. Just to illustrate this again, so what we got here is students will be most likely to take recreational breaks to manage their energy compared to full-time and part-time workers. And so what we got here is we've got, again, 81, 95, and 119 for 295 total sample. So those are the sample sizes. Here we've got our means. We've got 4.5 for students. We've got 4.2 for full-time workers, and 4.8 for part-time workers. And so we've got an F here, 9.1 basically. And statistical significance is SPSS is reporting it as 0.000. That's never going to be the true case. It's never going to be 0 exactly. So we're always going to be reporting this as less than 0.001. Get to that in just a second. Yes, Karam.
Yes, I have a quick question.
Yeah.
For the p-value, isn't it the rule that if it's less than 0.5, it's not statistically significant, and if it's more than 0.5, it is statistically different?
So in general, yeah, 0.05, not 0.5, 0.05. But yes, the way that is, I would say, is probably the most conventional way of looking at it, which means like that's the way almost everyone does it. In management, there's that in-between category where it's like between 0.05 and 0.1, where people talk about that as being, the language we used on the slides here is marginally statistically significant. People also talk about it as like, what kind of terms do people use as trending towards statistical significance, which is honestly the worst. I will take marginal over that. My general approach, like my personal approach, is if it's not less than a preset value, which in conventional terms would be 0.05. It is not statistically significant. Now, there are very, very competent statisticians like Val Johnson who make arguments that in fact that's far too generous. That what we should be using is a much lower threshold for statistical significance. So Val Johnson's argument is that we shouldn't be using 0.05, we should be using 0.005, which is much more conservative in terms of accepting statistical significance. And again, like part of this is just saying, for the purposes of this class, you can choose, as far as I'm concerned, whether or not you're going to accept that marginal category. And that one's a hard one to talk about because it's like, well, there's a little bit of evidence here that there is a difference that we want to talk about, but there's not that much. Whereas like, if you just use hard and fast rules, you can say like, nope. According to our criteria, there is no evidence here that these are different versus there is, and that's the thing, it's like statistical significance is just the data provide evidence that there is a difference between these groups. But it's not saying like that difference exists. It's not saying it's important. It's not saying anything like that. It's just saying like, according to the criteria under which we tested this, there is there is statistical evidence of a difference. And again, I get into the weeds on this, but it's just because I take it really seriously. Like statistical analysis is kind of my bread and butter. So so I'm trying to say like, hey, you know, the stuff that's written on these slides, go ahead and go for it. That's fine. You can do that, especially for the purposes of this class. But people are getting stricter about it. Like, so for instance, I'm a senior associate editor at Leadership Quarterly, and like the editorial team that I'm a part of, we would not let you get away with talking about this marginal significance thing, like a p-value between 0.05 and 0.1 as being like kind of significant. Like at that journal, that just would not fly, because the senior the editor-in-chief is very opposed to that, and most of the editorial board is opposed to that. So like if you were trying to write a paper on leadership and use that language, we would not let you do that. Whereas something like this slide right here, where the p-value is teensy here, like p way less than 0.00, like less than 0.001. That's definitely statistically significant, and can like pretty much anyone will let you talk about that difference. Like people might rip you apart for other aspects of your design and things like that. But this would pass first semester amongst pretty much any statistician or researcher. Even researchers who only know statistics but are not statisticians. Does that make any kind of sense? Sorry, because this part can, like, this is probably one of the most confusing things that we will deal with here in this class, and I want to be clear. This is a thing that like well, I've published material on this, and I'm a co-signer on a highly critical article about the use of p-values that was published in the journals. This was the Science or Nature now. I already forget. It's only been a couple of years, but like one of the two most prestigious journals science journals in existence. Again, I didn't write the article. I was just a co-signer on it, like, which means like I was a part of a group that the authors solicited and said, "Hey, do you agree with this?" And I was like, "Yes, I do," and so I signed it. So like again, it's a much more influential article than anything else that I've ever personally written. I didn't write it. I just said, yes, I agree with this in a public forum. But again, it's very much built on the grounds that this material is very confusing even for scientists. And so amongst those of us who are highly statistically literate, should we be pushing it? And the answer here in a class like this, where I'm teaching you, is that this is the conventional way that things are done in management. If you want to be a manager who's able to read the kinds of white papers that you're going to get from technical consultants or other consultants and those things, this is the kind of information that you need to be able to digest. You need to know what these words and numbers mean. And if you don't, you're going to be at a disadvantage, at least currently. Now, what I'm saying with that is, like, is this 100% right? I'm taking care to make sure that nothing I tell you in this class is technically incorrect. It may not be best practice in some cases. Like I said, with that marginal significance thing, like that is not a statistical concept. That's purely, well, in fact, like the level to place your significance threshold, like whether it's, I guess the question just a moment ago was like whether it's 0.05 or 0.005 or 0.01 or whatever, that is completely arbitrary. There is nothing, there is no God-given number there. It's just etched in the stones of nature. But that's where statistical significance happens. In fact, like we usually choose 0.05 because of an offhand remark that Sir Ronald Fisher made in like 1905. It means nothing. It was just sort of his guideline for like, if you got no clue what's going on, here's a good number to use as the basis of judgment. Sure, that's what we do in general. And that goes across like a huge range of sciences and empirical studies. So, so like the number there, like the 0.05 number, if you keep that in mind, as you like, you can read like a ton of medical studies, psychology, sociology. Like you can read most non-physics and chemistry papers. And look at the statistics and have the statistics make sense. Like maybe the science background may not, but like looking at the statistics, like if you can get the science to the point where you understand it, you can look at the statistics and evaluate it for yourself, because the statistics are always the same. And they're used the same in all those disciplines. Like the very, very, very hard sciences use the statistics a little differently. Well, a little differently in a highly meaningful way. But since most of us are not going to be worrying about physics, I'm not going to get into that. Just to understand that although these numbers and approaches are essentially arbitrary, they're arbitrary in a way that gets used everywhere. So knowing like the 0.05 and like if the p-value is lower, is that or lower, you'd be like, my work here is done. It's statistically significant. I've shown that there's a difference between these groups. Hallelujah, let's move on. Whereas if it's bigger than 0.1, any group you can be like, well, nope, that didn't work out. There's no difference here, or at least the data didn't show there was a difference. We got to move on, look for something else. The one place where management might differ from a couple of the other more like deeply scientific fields, like say biology, is that marginal category between 0.05 and 0.1. And like I said, that's not a quote unquote real category. It's just one that people have agreed exists. So you can talk about that as being marginally significant. But I'd say like from a scientific standpoint, you'd always be better off just sticking with the less than 0.05 and 0.05 and over in terms of valuing this as statistically significant versus non-statistically significant, respectively. That would be the best in quote unquote in the wild. But in this class, you can use all three categories, and in management specifically, you're probably okay with using all three categories as long as you're careful about it. Like we're trying to publish something. And let's just take a quick look at student satisfaction at John Molson School of Business with some data that have been collected over the years. So here we got, a handful of different majors. We got HRM, management, marketing, and finance accounting with 17 HRM majors, 25 management majors, 19 marketing majors, and 20 finance accounting majors for a total sample size of 81. So this is not a big sample. And right next to them, we got a mean of 2.5 for HRM, 2.2 for management, 2.6 for marketing, and 2.5 for finance accounting. And again, this is satisfaction with personal growth. So here we've got our F is 6. And our our p-value is 0.06. So with this one, we've got, using the symbols that we used earlier, this is marginally significant. So there's basically what this is saying is there's not huge differences. In fact, what we'd say here is, I would guess, pretty much this would be driven by the fact that HRM, marketing, and finance accounting are almost identical, and management is a bit different. It's a bit lower, but not hugely lower for the sample size. And that's one thing to keep in mind with statistical differences is you could have very small numbers of samples and a huge difference. But it may not be statistically significant just because the number of samples you have is very, very small. Whereas you could have a very small difference and a huge number of samples. And that might be statistically significant just because with several thousand people in your database, even small differences can be meaningful, or at least appear meaningful. So those are the things that are going on here. So Karam, go ahead.
Sorry, I'm just a little bit confused.
Yeah.
So now it's 0.061. That means it's greater than 0.05. So doesn't that mean it is statistically significant?
No. Statistically significant, to say something that is unobjectionably statistically significant is it's less than 0.05. So it has to be in 0.05 or a smaller number to be statistically significant, not larger. That's something that does throw people off. People get confused about that. Because again, what we're looking for, with this is saying, with statistical significance is you can think that what we're looking for is something rare. Because the default, again, is, let's say, again, the idea here is let me draw something that looks a bit oh boy, that's awful, but a bit like a normal distribution. So here in the middle, this is 0. This would be what would happen if there was absolutely nothing going on. And so then what we're looking at here is in this kind of high probability region, this is stuff that's close to 0. So these are the kinds of events that have very high probability. But over here, these are events that have low probability. And that's what we're getting at here, because the null hypothesis is always centered right here at 0. And so the idea here is if something has high probability, which is what the p-value is, it's a probability index. It's saying it's something that's comparatively close to 0. Now with the idea that actually as far as this goes, it goes way out is what we consider close to 0. So even things that have what appear to be low probabilities. So again, probability of 0.1, which is a 10% probability, is still high in a p-value consideration. Whereas something over here in the edges, with if it's one-sided, which we'll talk more about when we do the tutorials. And if it's one-sided, this is 0.05. If it's two-sided, so we're splitting this up because we evenly, because we don't know which side matters, 2.5% on either side. But that's the thing. It's so low p-values are very low p-values are what is significant. So this one here, in this case, which let's just change the color. So this p-value, the significance over here of 0.061, this is in that region that the picture shows here, that we called in this class marginally significant, in that it's between 0.05, which is the threshold for being definitely absolutely statistically significant in the conventional sense, and the 0.1, which is the threshold. If it's above that, it is definitely not statistically significant in the conventional sense. So it's in between those two. So if you want to talk about this as being marginally significant, you're more than welcome to. Formally, I would say from a traditional Neyman Pearson statistics perspective, this is not statistically significant because it's above 0.05. But because it's less than that, that 0.01 threshold. People in management and other social sciences sometimes treat it as if it's like kind of statistically significant, which is again, like for the standpoint of the discipline, fine to do, but from the standpoint of like the actual statistical reasoning is probably not correct. Then they should just, like if you're going to do that from like the standpoint of traditional statistics, you should just set your alpha level, the sort of like your level of statistical significance at 0.1, in which case you just say anything less than 0.1 is statistically significant, anything greater than 0.1 is not statistically significant. But again, I don't want to overthink this. I just want people, like for the purpose of this class, to go back to that other slide and just be like, if it's less than 0.05, it's definitely statistically significant. If it's greater than 0.1, it's definitely not statistically significant. If it's in between, it's marginally statistically significant, which can translate into kind of being like, it's come see, come saw, right? It's like in between those levels, it's like, it's kind of significant, but not really. So like maybe there's some evidence for it, maybe there's not. Does that make sense? Like I worry that the marginal one is what's really going to trip people up here, but it's something that because people do it in management articles, we need to talk about, even though it is probably deeply incorrect in every possible way. But people do it, so it's worth understanding it, because like for the purpose of this class, you may encounter it. Any worries, any questions so far? And again, like, don't worry about it now. Like, I mean, if you're having problems with it now, feel free to ask questions. But if we'll be working on this for weeks in terms of interpreting and using this sort of information. So like, if it's difficult now, that's kind of okay. Like if it seems easy now, that's definitely okay. But if it's still a little difficult, probably don't worry too much. We'll keep going over this and ask questions as they make sense to you. But if this is just like a mind screw and you can't get it, then definitely ask questions, because it's well, the other thing is, I remember like the very first time I taught statistics to an MBA course, like one of my students came up to me in office hours and she's like, when you're talking in class, this makes perfect sense, but then I go home to do the homework and I get fucking lost. Like, okay, that's good information. So like, this may all seem to make sense right now in the moment, and then you may try to go and do this, and it may be challenging. And if it is, don't hesitate. Like, if you go to apply this, or even if you just go to read over these notes and it doesn't make sense tomorrow or later on in the week or next week or whatever, don't hesitate to ask questions, because it is this is something that people have trouble with. Like, even like I've alluded to already, if I haven't outright stated, that even professional scientists have difficulty with this concept. They screw it up when they're talking to the media all the time. So it's very challenging. Like, you honestly need to get it like down to the point where it's second nature. You honestly need propaganda and indoctrination. Like, you have to be inducted into the church of classical statistics for this to seriously make sense for life for most people. Like some people like are just going to be like, oh, there's a rule and I can do it. But other people are going to be like, I need to make sense of these rules, and it's really hard to make sense of these rules, and I can't put them into any kind of a framework, and it just doesn't make sense, and now it's falling out of my head. And that's okay, because that's what happens to everybody. Everybody who gets this, that happens to them for a while. And so if that's happening to you for a while, like a week, maybe even two, don't worry too much. You can be okay. But ask questions. Don't be afraid to ask questions. And on that note, with this incredibly messed up slide, just moving on to predicting employee attitudes. So here we've got work status, which is part-time versus full-time employee, and gender, male versus female, predicting two different employee attitudes. So the affective commitment and loyalty to the firm. So what we've got here is, as our dependent variable, we've got loyalty, and we've got our full-time, part-time variable here. So we've got 124 full-time employees, right there, 124, and 41 part-time employees with a mean of let's just say 3.14, similar to pi for full-time employees, and 3.05 for part-time employees. We've got a t value, and again, we're going to ignore all the stuff to the left of this. We've got a t value of, let's say 0.66 with a p-value of 0.55. And again, if we wanted to say, like, the hypothesis here is full-time employees will be more loyal. So that's a directional hypothesis that's saying that full-time employees will be more loyal. So this is the two-tailed significance test. Now in JASP, I'm going to show you when we do JASP, you'll be able to set this up so it just gives you the right answer. But with something like, if you're ever forced to use SPSS, it doesn't allow that. So you've got your two-tailed significance test. If you have a directional hypothesis, all you do is divide that in half. So what we've got here is the one-tailed significance would be 0.255. So 0.26 here. And you can see that's just 0.511 divided in half. And again, in this situation, all that means is it's not significant however you look at this. Whether we're not sure whether the full-time employees or part-time employees will be more loyal, which is what this one translates to, not significant. If we're literally saying this, like full-time employees will be more loyal, it's not significant either, because this is greater, this number right here, 0.255, is a larger, substantially larger, 0.05, 5 times, more than 5 times larger. Let's take a look at this one. Hypothesis: women have higher affective commitment than men. So we're trying to write this in user-friendly prose. Don't worry about asking for volunteers, because that's from when we do this in person. I'm not going to ask people to do this right now. All we're going to do is look at it. So we've got 77 men, 88 women. We've got a mean of 3.2-ish for men, and a mean of almost 3.4 for women. So women have higher affective commitment than men. So in sample, yes, that's true. Look, we've got women have definitely, the mean is higher by like a decent amount here. So let's go to the videotape and say that. Sorry, that's becoming a less and less relevant thing to say. Okay, so here's our t value, and again, we're just going to look at this top one. The details between these are pointless to ask about right now. So we got minus 0.12 thereabouts. So our two-tailed significance test is 0.219, right? Okay, what is that? So that's 0.22 basically. So that, we divide that in half, because it's the same, women have higher affective commitment than men, which again, our means show that women score higher on average than men. They got 3.4 versus about 3.2. And okay, in two-tailed, that's not significant, divided in half, which is about 0.22 divided by 2 is, well, again, about 0.11. And so that's above 0.1, right? So that is not statistically significant. So what we conclude here is there is no evidence in this data that women have higher affective commitment than men. That's not saying they don't. Again, our means show that they do in sample, right? Again, the mean here, this number is bigger than this number, but it's not bigger by a lot. And again, our sample size is not huge. 77 plus 88, that's not a big number. That's not huge. I mean, it's decent size. I'm not knocking this for its sample size. Again, looking at something that's, on the order between 150 and 200. That's decent. That's decent for a t-test. But what we've got here is just there's whatever difference that we're observing is not big enough to rule out sampling error, chance, measurement errors, all those other sorts of things, right? So again, like all the other random factors that could affect this, that could stack up on one side or the other. So women are in fact higher. Like that's what the means show. So that is like the means themselves are consistent with the hypothesis, but then our statistical test is not showing that that is the case. So women are not higher enough on affective commitment to conclude unambiguously that women have higher affective commitment than men. And that's kind of what's going on with these kinds of statistical significance tests. They're just trying to show us whether or not the groups are different enough for us to conclude that they're meaningfully different. Look at one last domain here. So hypothetical research, dog owners' feelings of physical safety. So common errors in reporting results. And this is important because this is stuff that students get it wrong. So like we got as a predictor, we got our breed of dog over here, and we've got type of dog training. So professional, trained by the owner, or no training, and the owner's perception of physical safety. So our hypothesis examined the relationship between dog owners' feelings of personal safety and the breed of dog they owned. Dog breed is a nominal variable and feeling of safety is an interval, blah, blah, blah. So all these kinds of things that we've talked about in this class, like I said, they're not actually important like last week. So nominal versus interval versus whatever variable. Like when you're writing up your results, you are not providing a statistics lesson, right? So like you're not going to tell people this stuff. You're going to report things. So what we're going to say here, instead of like dog breed is a nominal variable and feelings of safety is an interval variable, the test used was one way I know, but you're just going to say like you're just going to say like our hypothesis examined the relationship between dog owners' feelings of personal safety and the breed of dog they owned, and then you might describe the levels of that. So again, let's go back here. So we've got 3 levels, or actually we don't have it here. Let's just say we had like large dog, medium dog, and small dog. You would just describe that. You would say my breed of dog was broken down into 3 types of breeds: large dogs, small dogs, and medium-sized dogs. And then you might describe the actual measure that was used to evaluate feelings of personal safety. You wouldn't even bother saying this was ANOVA. You would just report the F statistic and its p-value. And then you'd say, once you've done that, well, again, like all you would do in like a results section is report that. But you'd also report things like descriptive details of the statistical analysis. So you'd report how many people owned, let's say we had large dogs, small dogs, and medium-sized dogs. You report the number of owners who were in each category and the means for each of them, the F statistic, and the p-value. That's what we would do here. You wouldn't, like, this other stuff is unnecessary and just complicates things and provides, I mean, the idea here is like, I'm not saying it's never appropriate to provide a statistics lesson in a research report. I have written several papers that have statistics lessons in them personally, but again, they are using statistics that I am highly confident that my audience knows little to nothing about. And that's when it's appropriate to explain what you're doing, to the point where like explaining the statistics is an integral and important part of the paper. Whereas if you're reporting basic statistics, you do not have to explain it. Like you can operate under the assumption that your audience is going to know what's going on. So on that note, let's just go through some more. common things. So common errors in reporting results. Do people feel more secure if they have a big dog? Boom. Good question. 45 respondents own big dogs like Rottweiler and Doberman breed. I would say breeds here rather than dogs, but again, so we're saying the number, and you'll see here, this one, this number, like since this is the start of the sentence, this one's written out. Oh, come on. That's written out, whereas then this one here, 38, since inside is used as just in numerals. That's fine. That's the way it was on small dogs like Chihuahuas and toy poodles. A t-test was performed to determine whether a relationship existed between the type of dog owned and the owner's percent. So in this case, we're just talking about large versus small dogs. We should report the means here. So we should say, like, what is the mean personal safety for these 45 people and the mean personal safety for these 38 people. We shouldn't, in the results section, be talking about things like strong. We should just say the test revealed that there is no relationship or no statistically significant relationship between the type of dog owned and the owner's perception of personal safety. So minus t equals minus 0.67, p equals 0.51. You should probably put your 0 in here. And again, this is just showing that it is not statistically significant. Again, here to get kind of like at the essence of what we were talking about before, this one is saying very, very clearly, like, there is no statistically significant relationship. Sorry, this is just 0.51. I was thinking 0.051. But again, this is just not statistically significant. And here, final set of reports and result errors in reporting that I'm going to deal with today. The participants reported the extent to which their dogs were trained, the variable training. Don't use your internal labeling for results. Like that's not the way we're going to do things here. We're going to talk about variables with their kind of natural language names, and it doesn't matter which question number they appeared on. So here the variable training was measuring question number 8. It doesn't matter. That is irrelevant to the reader. Under most circumstances, like maybe if you were actually doing a study on question order, it might matter, but under normal circumstances, no. It doesn't matter whether you coded professionally trained as 1 or trained as 2 and not trained as 3. That doesn't matter. It matters that you had professionally trained, owner trained, and not trained. The numbers you use, that generally doesn't matter. Perceptions of safety, it doesn't matter which questions they were measured as. All the you want to make sure that variable labels, question numbers, and coding labels, those it's important, as it says here, to view those as conveniences for you as the researcher. But in general, those don't matter to the reader. What matters to them is the conceptual labels. So you need to make sure what those things represent. And in general, like, you're almost always going to wind up reporting your numbers 1 decimal place. Anything else is more precise than is necessary for the kind of reporting that we're doing. So like maybe under some circumstances 2 decimal places, maybe occasionally the p-value up to 3, but almost under most circumstances you should round to 1 decimal place because of precision issues. Like, we just do not measure things precisely enough to report to 3 decimal places, or even 2 under most circumstances. So typically round to 1 or maybe 2 places, depending. Like if you have a really big sample size, maybe 2. If you have a pretty normal sample size, just 1. And so I'd say for this class purpose, when you're reporting the results in the assignments, just 1 decimal place. I'd say honestly, that's everything that we should talk about in today's class, especially since it's now 5:30 and I need to let you guys go. I see I've got 1 message here. Well, yeah, okay, sure. I will talk about, when I post some additional materials, I'll talk a little bit more about the right way to report the results from the dog study. Anyways, on that note, I think I need to let you guys go, and thanks for coming today.
Hi, sir.
Yep.
How's it going?
Yeah, doing all right. You?
Hey, that's good to hear. I'm doing well. Yeah. So, how's your mother-in-law doing? Is she getting better?
She's apparently, like, it was a touch and go, but apparently she has settled down into an infected but asymptomatic state, which is pretty awesome for someone who's 91 years old.
Oh, that's good. Good to
Yeah.
hear.
Like,
So,
so she's still in isolation, but she seems to be doing all right. Thanks for asking.
okay. So that's good to hear.
Mhm.
Yeah. So I had a proposal to make.
Yeah.
So, with the midterms and other big assignments piling up
Yeah.
for other classes, like I was thinking perhaps assignment one can be scrapped and the
Well,
marks can
assignment
be
one,
given
it's
to
not going to
us.
be. I'm not going to scrap it because it's going to be important for you to learn things. But again, like I said at the beginning of class, like the assignments are for learning purposes. So you shouldn't worry about your grades on the assignments because
No, it
unless
just had to do
unless
more
you
with like the workload, like
well no
in the.
again the workload I'm going to stretch out the deadlines for things but I think it would be remiss of me not to have you do it. Um, so just there, actually, sorry, I just got a message here, and there is no direct update for assignment one. I'll be posting everything about it. God God willing, tomorrow morning. So I do have a bunch of meetings tomorrow morning, but before those, I'm going to get that up. So there's no specific update right now, but I hope to get to that before 10 a.m.